and I want to make sure that it is recording the way I want it. Oh, the mic is definitely not on. Okay. Alright, so I'm gonna stop it first. Actually, make it. I wonder which mic it's using. It's using both mics, which is not good. Okay, I'm gonna exit from here. There we go. Okay. So with the recorder on, I'm gonna go back here. I'll compile the program first, because we're gonna get back into the code anyway. Dash O argc. There we go. And I'm just going to use the debugger, GDB, to look at the behavior of this program. So when I run this program, I just want to put a breakpoint on line 3, so I have a place to stop, so I can show you what argc and argv are going to look like. When I run the program, okay, you guys can't see the bottom. So when I run the program, I can pass the arguments as if I'm running the program from the command line. So I can just run it with 2 and 3, just like in the example in the assignment. Okay. So when I press the enter key, it will get into the program, hit the breakpoint on the only one statement in the entire program. So right now I can print argc, which is 3. Now you might ask, why is it 3? Because there's only 2 and 3 as actual arguments, right? Well, by default, the first argument is always the path to the executable itself, which is not useful to you. So that means argv1 and argv2 are the two elements that are useful to you. argv0 is typically useless in this type of program. Okay, next thing. I want to print argv. Not very useful, because all it's going to say is, oh, argv is a pointer to a pointer, which is the same thing as an array of pointers, right? But you can also just do your own indexing. So argv0 in this case is not really particularly helpful. It just shows you the path to the program itself, which is in the temp folder, and the name of the program is arg. Okay, so that is not going to be useful from the perspective of your homework assignment. The other two, on the other hand, is what you need. So argv index 1 is giving us the 2, and then argv2 is giving us the 3. So are we okay so far? You can assume that I won't trick you and pass things that are not numbers or numerical, or the wrong type of numerical. So I'm not going to pass like -2 or 2000. I will make sure that everything is between 1 and 26. But even if you make that assumption that it is always between 1 and 26 in base 10, you still want to know how to do the conversion from string back to the actual numerical value. There are several ways to do it. So to do that, one way to do it is to use ATOI, ASCII to integer. Okay? ATOI belongs to the standard library header. So you have to do the pound include stdlib.h if you want to use this particular function. So ATOI, is ASCII to integer. ATOL is ASCII to long. I would just advise you to use ATOI because we are not dealing with really big numbers. So what you do is you pass it a string, and it returns the numerical value. Pretty easy to use. And it does make the assumption that it is in base 10, which is what we're going to use in this program. So is that okay? If you're using Node or Python or other scripting languages, that conversion can be done differently. So you kind of have to look up how to do it. In some scripting languages, it's just a context. Okay, if you start to use a value as a numerical value, it becomes a numerical value. Okay, so it depends on the scripting language that you're using. Are we doing okay so far with this part? Are we good? Okay. Is anyone going to use Java for this particular program? Huh? I can add it. I don't think it's going to buy you anything, if you use Java versus C++, it's about the same. But if you want to use it in Java, you just have to kind of look it up. I think the mechanism is pretty close, but not exactly the same. JavaScript would need to use the process module to get to the arguments, so it's a little bit different. But if you just look up whatever language you want to use, okay, let's pick a Ruby, okay, which is not on the list, okay, Ruby on Rails. And if you want to look up how to do this, just look up argc and look up argv, okay, that's how most people refer to the arguments. Okay, so most programming languages, even ones that are like really, really not close to C and C++, but still kind of, use the same kind of names. Okay. Are there any questions about how to get to the arguments? No questions? Okay. So if there are no questions about how to get to the arguments, the next question is, how do we generate this kind of output? So the first thing you have to think about is, do you want to maintain a list or a set of all of these combinations? Or do you think that you can just kind of keep track of the partial combination being generated and work with that and using recursion to do it? Okay, so there are different alternatives to do it. You kind of have to choose one way or another, okay? The best way to work on this is to do it by hand first. Okay, use very small numbers of items to, and also small number of trials, and then just do it by hand. Okay, so I can show you what I mean by that. So to do the example by hand, okay, so let's say we are using 3 outcomes for the first trial, and then 2 trials per experiment, okay? Which is the same thing as the example I use in the assignment description itself, okay? I want you guys to use lowercase letters, as the outcomes per trial. So we have a set of A, B, C, okay? So for the first trial, okay, for the first trial you can use A, right? You can use B, you can use C. Now, for the second trial, so I'm going to have to do it a little bit more inventively here. So this is the second trial. So for your second trial, because we are talking about combinations, once you have chosen A for the first trial, your second trial can use C, B, or you can use C, right? Okay. So now you have, okay, let me use one more column for the entire outcome, for the experiment outcome. So when you look at the experiment outcome, okay, once you have A, B determined, we're done. Why do we know we're done? Because I said that you only have to give me outcomes of experiments with 2 trials. So once I have chosen the first one, A, once I've chosen the second one, B, I'm done with that experiment. And the combination output is AB, okay? So that's easy. Then you look at AC, and the first question is, can AC be something that we have seen already? The answer is no, okay? So we have AC as the outcome as well. Here comes the tricky part. If you're in your recursion, you will go back to this case, okay? And you ask, what can B be combined with? Okay, the first one is BA, right? Okay, if we think about permutations, the first one is BA. But we don't want to put BA as the actual experiment outcome because it is actually the same as AB. Because we are talking about combinations where ordering is not important. So AB is already printed, it's already done. We don't want to put BA into the set or into the output, okay? So, well, I'll just kind of indicate that this is not something that we want, okay? But then you can also combine B with a C, right? Have we seen a combination that has B and C in it? Nope. Okay, well, BC is another possible outcome, as a combination. So now here comes we have C, okay? Do you think that there's anything we can combine C with that we haven't seen before? No, because we have tried out everything already, okay? Everything that starts with A, everything that starts with B, and if we consider everything that starts with C, it's going to be something that we have seen already, okay? Because CA is already here, okay? What about CB? It's already here. So that tells you something about this exercise is actually not as complex as what you think it to be, because ordering, because A, B, C, all the alphabet letters, they are totally ordered. Yep. It is without. This is always without replacement. Well, then you have a problem, because if you're saying with replacement and you're talking about combinations, then A is really just A. Yep. So that those two concepts really do not mix. Yep. Or you can mix them, but A would not be a possible combination because it only has one element in it. So do we have any questions about, like tips of how to get this program started? Yep.
So once we do every possible combination with A as the first letter,
Mm-hmm.
we know that there's no other possible combinations with A.
That is correct.
Okay.
Mm-hmm. Yep. Once you get all the combinations done with B, starting with B, then you know you're done with all combinations that involves B in some way. So that's a very good observation, because that can help you optimize your program and simplify the logic of your program by a great deal. Okay, I'm not going to spell out the tricks and whatnot, because that really is a part of the homework assignment. Because by doing the homework assignment, you start to gain an insight of how to generate these combinations. All right. So you got a week to work on this one. Yep.
Can you add Java?
I can add Java. Sure. The only time I think people are preferring Java would be people who are transferring to Sac State, because Java is used at Sac State as the standard language, as opposed to C++ for most other universities. But I can add it here. I was tempted to add a TTP ASM to it. I don't think we have enough resources in the TTP to do this with 256 bytes.
May I add some extra credit?
Huh? Make it extra credit. That would be a good topic for a programming contest. Yep. All right. So are there any other questions about this homework assignment? So once again, don't think in coding first, okay? When you start to work on this project, unless you have already thought about it and you have a pretty good idea to start with, if you're thinking, I don't really know how to get started with this program, do it by hand first, okay? Just do it by hand. Pick some examples like, four outcomes and 2 trials, okay? That is totally doable by hand, okay? And as you do it by hand, you will start to notice patterns. It's like, oh, I can optimize that, or I can optimize that, or I do not really need to represent each set as a set. I actually have a much quicker and easier way to deal with this. Okay. All right. So that's your homework assignment. It's due in a week. I think it's definitely doable in a week. But if you run into a snag or somewhere you don't know how to proceed, you can always come to my office hour, or you can bring the question up in the next class. So there's that. All right, so we can now proceed almost past counting and discrete probability. Okay, we are almost done with this. We never really finished the Powerball discussion. Okay, so let's go back to the Powerball discussion. But first, remember the first step. What was the first step to play Lotto? Powerball? Dream, I think. Yep. Well, there's a big difference between believing and dreaming. Dreaming at least knows that it is a dream. Believing is a slightly different thing. Huh?
You say you don't
so we'll go back to the Powerball homepage. And is this the California Lotto? Nope. 750 million for the estimated jackpot. Imagine. Okay, so this one says imagine. And here's a new egg, business advertisement. Okay, so what I want to do is to figure out the probabilities of winning the other prizes. Okay, so here we have all the prizes, and they're coding everything in a slightly, to me, confusing way. So to win the jackpot, you will have to match all 5 lucky numbers and the Powerball. Okay, that's how you get the jackpot. To get the second prize, you have to match all the lucky numbers, but you do not match the Powerball number. Okay, and to get the third prize, you match 4 of the 5 lucky numbers and the Powerball, and so on. Okay, so do we understand how to read this table? We good? Okay. So let's just say that, I am interested in, okay, what is the payoff, whoever is organizing, this lotto, how much money do they have to pony up, okay, for each round of, playing this lotto, based on a certain number of people playing. So now I need to understand, out of, all the possible tickets, how many tickets will match just the Powerball by itself? Okay, because that number multiplied by the prize money, which is $4, will give me an estimate of, okay, I need to pay off this many people with $4, right? Then I need to figure out how many people would match 1 out of the 5 lucky numbers and the Powerball, and those people also get only $4. Okay, so I need to kind of come up with that probability distribution. So how would I do that? So that becomes the next question. How do we do this? How do we analyze this problem so that we can solve for those numbers? Okay, so I'm going to scroll all of these out of the way, and then we ask the question, okay, what are the odds of just matching the Powerball? Okay, so I'm going to put this, as just matching the Powerball. Okay, how many numbers are we choosing from the Powerball? How many alternatives are there for the Powerball number? I think it's 27. Huh? It's 69 for the other 5 numbers, but I think the Powerball has to be chosen only from 27 numbers. Okay. So, but wait, the problem with this question is there's a hidden component. The hidden component is not really just the odds of matching the Powerball number, but also matching none of the lucky numbers. Okay? So here's the part that is missing. Matching none of the lucky numbers. But we match the Powerball. Okay? So the probability is not really just 1 over 27. Okay? Assuming we choose the Powerball number out of only the first 27 numbers. The actual odds of this is a little bit more complicated because we have to figure out how many ways can we choose 5 numbers and none of them match any of the lucky numbers. That becomes the tricky question. Okay? So assuming that we have 69 numbers to choose from, 5 of which are the lucky numbers, right? So how many lucky numbers are not lucky? 64 of them. And out of 64, we need to choose 5 of those. Is that okay? So that means that is what we need to deal with here. So we need to look at the combination of choosing from the 64 numbers that are not the lucky numbers. And of those, we need to choose 5. And there are this many ways to choose from the not lucky numbers. And then we have to, and then we have to divide it by 69, choose 5, which is the total number of total number of ways to choose 5 numbers from the 69. Are there any questions about this number?
65?
Huh?
65 or 64?
It's 64 Wait, okay, I can't do my math. No, 64 is right because there are 5 lucky numbers.
But you have 64 and 60. Oh, okay, so you're subtracting 5 from the 69.
Right.
Okay.
So if I want to be absolutely clear, this is coming from that. Because we are looking, okay, but there's one more, okay? If you really insist, and which is actually useful, is we are actually choosing 0 out of the 5 lucky numbers. So it doesn't really do anything to the equation because choosing, oops, I got it flipped. Choosing 0 out of 5, okay, there's only one way, okay? There's only one way to choose nothing out of any number of things. So the combin 5, 0 doesn't really contribute anything to the overall value, but it is still useful here because, we'll see there's a pattern as we work on the other ones. Is that okay? So this is the overall probability of somebody getting $4 back because that person matches only the Powerball number and none of the lucky numbers. Is that okay? Sorry? I can use a spreadsheet to calculate it.
Bad odds for getting $4.
Okay, so I'm going to use a spreadsheet to do this calculation. Let's see here. Yep, that's a letter of recommendation. All right. So we are looking at the number which is 1 divided by 27, which accounts for the lucky number itself, the probability of choosing the lucky number. But we also have to look at the combination of choosing none of the 5 lucky numbers combined with choosing 5 out of the 64 non-lucky numbers, and then dividing it by the total number of ways to choose 5 numbers out of 69. Okay, so we have 69 and 5 here. And that turns out to be 2.5%. So yes, so there's a 2.5% chance that somebody may get that one prize, okay, which is $4. And I think we can assume that it's $1 per ticket, right? So that means it's not really that good of a payoff. You pay yeah. It's $2. Oh wow. Okay, that makes it even worse. Okay, so let's work on the next one. Okay, so now that we know how the first one works out, the next one should be fairly easy to work on. So this one is based on matching one of the 5 lucky numbers and also matching the Powerball number. So let's see what we can do to calculate this one. I'm just going to do a copy and paste because the equation is very similar to the other one. So the way we modify this is we are choosing one of the 5 lucky numbers, and then we are choosing 4 out of the 64 non-lucky numbers. That's the only change. Is that okay? Huh? Why? There are only 26 numbers to choose from for the Powerball. Let me.
Can you say what the equation is one more time for me?
Yeah, I just want to check one more thing. Which is how many numbers do they choose from out of the Power? Out of how many do we choose for the Powerball? Is it 26 or 27?
Yeah, that is what it says.
Where?
If you just look at Powerball on Wikipedia.
Oh, okay. So how many choices for the red ball? 26? Okay, we'll modify the equations to do that. So that improves the chances just a little bit.
2.6.
Yep, it's now up to 2.6. Yes.
Yeah, here I come.
Yep.
Gonna win the lottery.
Yep. Okay, so you guys want to display the equation? So the only difference between the first one and the second one is in the first one, we are choosing 0 out of the 5 lucky numbers, and then we are choosing 5 out of the not lucky numbers, the non-lucky numbers. Okay? And then with the second one, we are choosing 1 out of the 5 lucky numbers, and then we are choosing 4 out of the 64 non-lucky numbers. Is that okay? Are there any questions about why we are multiplying instead of adding? Okay, because it has to do with, for each way of choosing 1 out of the 5 lucky numbers, there are combine 64 ways to choose 4 of the not lucky numbers. Okay, so it has to do with the use of the word for each. Okay, so I think from here on, it's going to be pretty smooth sailing. Okay, because in this one here, we have to match 2 of the 5 lucky numbers, right? So we just up this number from 1 to 2, but that automatically makes this one a 3, because out of the 5 numbers on the ticket, 2 are now taken care of because they have to be the lucky numbers. So the remaining 3 numbers are coming from the not lucky pool. And that changes the chances to only 1.4%. Yeah. And you're only getting $7 out of 2. And if you work on the other ones, let's work out all of them. Okay, so this one says only 3 lucky numbers. Yes.
Did you multiply by 100?
By 100?
Yeah. So
Where?
you're finding the percentage, right?
Do you want to look at the percentage?
I don't know.
This is not percentage.
Oh, this is not, okay.
This is not percentage. Oh, I did it in my head. So the first one is 2.6%.
Okay.
Yep. But if you want to look at percentages, that's pretty easy. We just need to format the cells, go to numbers, and pick out percentage. There we go. So now you get percentages. Okay, let's work on the next one. We want to match only 3 lucky numbers. Okay, copy and paste. There we go. Okay, so if you want to match only 3 lucky numbers, the implicit thing that was not said is you did not match the lucky number. You did not match the Powerball number. Okay, so you only got 1 out of 26 ways to match the Powerball, which means you have 25 out of 26 ways not to match the Powerball. So that's why I changed the 1 over 26 to 25 over 26. But we also have to change the rest of the equation, because now we are choosing 3 out of the 5 lucky numbers and choosing 2 out of the 64 non-lucky numbers. And the chances is it went up a little bit, okay? And if you look at the prize money, does it went up? Nope, the prize money is still 7. Okay, next one. So next one, compared to this one, there's only one minor change. We have to match the Powerball number. So the 25 is now going back to a 1. The rest are the same. And the chances of doing that is only 0.01%. Of course, it's rounded, but it's pretty small. It's a pretty small number. Okay, so we're talking about this one here, which, if I remember correctly, the prize money was $100. Okay, so you use $2 to place a bet. This is the chances that you can get $100, because you won that prize. Okay, so at the end we'll do a summation of all of those numbers. Okay, so we will know, regardless of the jackpot, how much money we can expect on the average to come back from those $2 that you spent. Okay, so we move up to this one, which is similar to this one. In the sense that the Powerball number does not match. So this time we are talking about 4 of the lucky numbers and only 1 of the non-lucky numbers. So it shows you 0% chance because it's rounding, right? So we'll go back to do the other rounding. Okay, so we'll say let's not do percent. We'll just do numbers. Okay, there we go. Looking much better, right? Okay, so this one, you can copy and paste it to here, and then change the 3 to a 4, and then the 2 to a 1. So this one is matching 4 of the 5 lucky numbers and the Powerball number, okay? And then we have, I'm just leapfrogging here, okay? This calculation is going to be corresponding to matching only the 5 lucky numbers, but not the Powerball number. So now we have 5 choose 5, and 64 choose 0, and that's your chances. Those are your chances. And then we have this one copied to here. So now this is the jackpot, right? So the jackpot is easy because we are matching all 5 out of 5 of the lucky numbers and 0 out of 64 of the non-lucky numbers. So what we are doing here is both of these common bins become 1, okay? But it is still divided by 69 choose 5, which is a pretty big number. So as a result, the chances of that is 3.42298 times 10 to the power of negative 9. That's the chances of winning the jackpot. Huh? Yes. It's yeah. Okay. So now we multiply everything by the actual prize money. Okay, so we got 4, 4, 7, 7, 100, 100, 50,000, 1 million, and then the jackpot is, that's pretty high, 750 million. 1, 2, 3, 4, 5, 6. There we go. And then we look at the click. There we go. So we now look at the products of this times that. So yes, you might actually get a positive return in this case, given that is the jackpot. So for the $2 that you spend, on the average, you're getting $2.89 back. Before taxes, exactly. But I would, you can also look at the other number, regardless of the jackpot, okay? If you don't count the jackpot, what do you get? So for every $2 that you spend, you're getting 32 cents back. Yep. And that's regardless of the jackpot. Yep. Now, the problem with the jackpot is you don't know how many people have duplicate numbers. Okay? With all of the other prizes, okay, with everything from here to here, it has nothing to do with the number of people with the same number, who have chosen the same number. But the jackpot is divided by duplicate tickets. And unless you have a very advanced model to figure out, okay, with a jackpot of this much money, the number of duplicate tickets you can expect, then you really don't know whether this is going to be the amount that you're going to get, because it would just be split across all the people with that jackpot ticket. Does it make sense? Are we good so far? So how many people are still going to play lotto? In a way, I really like people to play lotto, because lottery funding, is actually important to community colleges and schools in general. But on the other hand, the numbers, kind of tell you something about, playing the lotto, buying a lotto ticket. So I think we talked about this already. At some point, it's gonna, there's an equilibrium, or there's a, how do I call it? There's an equilibrium point where you pay. Education has enough resources to educate X amount of people, and then there will still be enough people to buy lotto tickets to kind of. So it cannot swing any further, because if education has all the money that we need, then everybody will be informed of probabilities and distributions and stuff like that. So very few people would play lotto in that case. But in that case, because of the lack of lotto money, education will lack funding again, right? Then more people will play lotto again. And then with more people playing lotto, there'll be more funding to education, and then fewer people will play lotto as a result of that. So there's a swinging motion here. Yep.
Although there is a problem with it.
Yeah.
It's what kind of people play lottery. Or is it rich people or poor people?
Well, okay. To analyze that, we're going to go back to the article that I wrote, right? And you can actually find it online too. 150 million. And see, yep. All you have to type is 150 million, and you get this article. So these people, if you look up, what is the average, wealth of these people, it's crazy. No, it doesn't show you the numbers.
There's links to the
Okay. And also, by the way, those 400 people, they tripled their wealth from the 1980s to today. I don't think the average person tripled their wealth in the same amount of time. So anyway, all I can remember from the convention was, if you're a millionaire today, you're inconsequential. You actually belong to the rest of the people and not really even close to the top 400 wealthiest people. Well, if you play the Powerball and you win the $750 million, that gets you pretty close to being a billionaire. But then the IRS will come and cut your wealth in half right there, right? So, say that more time?
Put all your wealth in Monaco so that they can't tax it.
Yeah, exactly. Follow the top 400 people. Assuming they let you in, right? That's how, if you look at the taxation, how much we tax the top 400 wealthiest, people, I think there has to be records of, how much money we get out of it. Another article that's kind of interesting. Yeah.
When you say top 400 wealthy people, are these people where, like, they actually own that much money, or is it their company that?
It means if they cash out, they're worth that much money. So it doesn't mean that they have that much money as cash. But when they cash out all their stock options, they will be worth that much money combined. Yep. So on tax cut, it's interesting. I mean, this is one of the wealthiest people in the nation, and so his response to tax cut was, you guys really should tax me more because of the new tax law. I have just for no particular reason, made this much more money, and there were a lot of zeros involved. He was basically, think about this from his perspective. Do you think it really matters? Would it change his lifestyle, or what he can buy, what he cannot buy, what he can eat, what he cannot eat, if his tax rate goes up even by 30% or 40%? No. So so for somebody like that, it doesn't really matter anymore, because wealth to these people is no more than just a number. It does not have any impact on day to day, like, should I buy Starbucks today? Probably not. and this is my wallet, right? If you jack up his tax by 30%, I'm pretty sure it makes no impact whatsoever, okay? Or, should I drive to school? Should I bike to school today, or should I take a Lyft since I don't have a car, okay? Do you think it matters to him? Makes absolutely no difference, right? So that really kind of, it baffles me. It really baffles me how some of these billionaires, really want to privatize everything, including, public education, because public education nationwide is a multi-trillion industry. So there's still a lot of money in it, even if you were a billionaire. But if you were a billionaire, to doubling your wealth, what does it mean to you? It's something that I cannot understand because I'm not quite there yet. I'm a few zeros from it. It triples your wealth, but what does it mean to you? I mean, to us, it means a lot, right? It means, oh, I can afford to have sushi every day. Cool, okay? Or I can buy a car brand new car from a dealership instead of buying it from Craigslist, okay? So to us, it means a lot. It makes a lot of changes, whether you're doubling your wealth or not. But when you already have tens of billions of dollars, doubling your wealth is really nothing more than something on a piece of paper that says, oh, it's doubled. Exactly. You have to imagine. This is something way beyond my ability to imagine, trust me.
They're not human anymore. Their blood's made out of money.
Huh?
Their blood's made out of money.
Yeah. So that is something that I cannot understand, which is okay. There are many things I don't understand. All right. So are we good so far with the analysis of these numbers? Okay. So once again, okay, with a jackpot of 750 million, if you spend $2 to buy a single lotto ticket without considering tax consequences, you get $2.53 back. But with tax consequences, it's going to be a bit less than that. So are we good so far? Yes? Okay. So we are now done with counting and discrete probabilities. So that whole topic is done, and we can now move on to the next one. So we got a few choices here, okay, because the next topic has no connection whatsoever to probabilities. So we can start with predicate calculus. We can do graphs, or we can do the big O, little o notation. We'll do all of them, but we have the sequence, right? So which one do you guys want to go for next? Big O? I would say big O has more, is more useful. Graph is good, that's useful. Big O is useful too. Predicate calculus is useful from a theoretical perspective, but on a day-to-day basis, it is not as useful. So we can push that off a little bit. Okay. Let's vote. That's right. So those who want to continue with predicate calculus, raise your hand. Those of you who want to continue with graph stuff, which is Dijkstra's algorithm and A-star algorithm, raise your hand. So we got 7 hands. And those of you who want to go for big O, little o, omega, and theta, raise your hand. So I think the big O people, win in this case. Okay. This is the one thing that is really interesting about the Union Convention too, is, it's very democratic. So each school or each district, sends basically a team of delegates, to the convention. And then, whenever they have a resolution, like somebody can propose, anyone can propose a resolution. I can propose a resolution and say, I want to raise my own salary by 200%. If I do it every year, I might come close to a billionaire. It depends on how long I live. So I can propose anything as a resolution, right? So now they can put it onto the floor for debate and voting. Okay, so if a lot of people know me and they know that tech really deserves making twice the money compared to last year, they can all approve it, and I will get I can then the unit can move forward and try to get it done. Okay, but they everything is voted on. It's a very democratic kind of process, which is kind of interesting. All right, so we're going to get started here with big and little o, omega, and theta, which starts off with time complexity. So we are only talking about time complexity with all of this stuff here. There's a lot of math involved, okay, in all of this, and it can be very dry and boring. So before we go, we get into the math stuff, let's use an example and illustrate why this is actually important, okay? So let's just say that this is not 2019, it is 2022, and the Silicon Valley just collapsed because high-tech industry, the bubble burst, just like in year 2000, and companies have to downsize. So it's down to me and Pat as the only two employees left. I chose Pat because it can be any gender. Being politically correct. So it's down to me and Pat. And then the employer says, okay, we have to decide who is going to have to pack and go and who can continue to remain with the company. So the company organized a programming contest. It's like, okay, let's just do search, okay? The boss will give me an array, and I have to search for whatever item the boss said, okay, look for this item. And then it's timed, okay? And whoever, can come up with the answer the quickest wins, okay? Pretty simple rules, right? Well, there's only one little caveat from my perspective. Being a long-term employee, I'm still using that 386 computer that I started off with like 20 years ago with that company. And Pat, being a new employee, had a 18-core i9 processor in Pat's computer with 30 gigs of RAM and all kinds of goodies in it, okay? So I go like, well, that kind of sucks, okay? Because, a 386 is, let's see, the 386 came out when I was just going to graduate school. So that's about 89, okay? So how many years have passed from 1989 to 2022? 33 years, okay. So according to Moore's law, okay, things are twice as fast or twice as dense, okay, every 18 months. So how many 18 months do we have in 33 years? It's basically there are two Moore's laws cycle every 3 years. So there are 11 of those years, right? 22. That's right. Okay. So we are looking at 22. What 22? Is Pat's computer 22 times faster than mine? No. Pat's computer is 2 to the power of 22 times faster than mine. Because it's doubling, right? For each period of Moore's law, it is supposed to be quote unquote doubling the density of transistors. Okay? So let's just give it a discount and just call it 11, okay? 2 to the power of 11, which is about 2048 times, something like that, okay? So Pat, assumes, oh, I don't need to care about what algorithm, okay? I'll find the first and easiest algorithm to implement, and I'll still beat, tech. So we look up, search algorithms, right? Okay, search algorithms, and then we go for search algorithms here. And the first thing that pops up is sequential search. Okay, cool. You click on linear search, and Pat thinks, oh, that's easy to implement. Okay, if you just look at the picture. It's easy, right? It's just a little bunny bouncing, from one pebble to another pebble. Okay, or tacking or going from the island in an attempt to go to the cruise ship. Remember proof by induction? Okay, so I got to remind you guys of those things, right? Because otherwise you lose track of those. Okay, so linear search is easy. That's okay. And Pat decides, well, I need to look for the actual algorithm itself now that I know the name, right? So linear algorithm or linear search algorithm in C++. Okay. So easy to code. And somebody wrote it already. Cool. Easy peasy. Copy and paste. Done. Okay. But Tech decides to go a little bit further and look for the most efficient linear search algorithm. Okay, so Tech searches for linear search algorithms. Okay. And Tech decides to go to Wikipedia. There's always a tab open on Wikipedia somewhere. Okay, and there are many of these search algorithms. So out of these, Tech can look for, because the boss said everything is sorted in the array. So, Tech searched and go like, oh, okay. There's a binary search algorithm somewhere. Okay, where is it? Okay, here's binary search algorithm. And if you look at the algorithm itself, now we are not going to talk about the detail of the algorithm itself. And we'll just look for the, okay, so this is the binary search algorithm. Looks quite a little bit more complex than linear search, and if you look at any type of demonstration, it involves a lot of jumping around, so it seems a little bit more complex, and it certainly is longer, okay? So I chose to use the binary search algorithm. So here is the competition, okay? So I'm going to show you the competition result using a spreadsheet. So the first column is what we call the problem size. Problem size in this case is really just the length of the array, okay? So let's just say the array has one element, okay? And this is how long Tech's computer takes, and this is how long Pat's computer is going to take to, confirm one way or another whether, a particular key is in the array or not, okay? Well, with only one element in the array, obviously, Pat's computer will only need to go through one single iteration. And we'll use Pat's computer, iterations as a basic timing, unit, because it's just easier for me to keep track of things that way. Now, Tech's computer being a lot slower, okay, so depending on how much you trust Moore's law, okay, which is I'm trying to determine the performance difference between a 386 computer running at 33 megahertz compared to an i9 computer running at 4 point something gigahertz. Okay, so I would just be very conservative and just say that, let's see here, what would be a good factor to use? Well, first one is clock speed, okay? So we are talking about 4.1 gigahertz divided by 33 megahertz, okay? And then we times 2 because, the computer, the 386 is a 32-bit computer, and then the i9 is a 64-bit computer, okay? Just that alone is only 200 something times, and then but you also have to take into consideration double the DDR2, that sort of thing. So I think 2,000 times is not unreasonable. Is that okay? Okay. So Tech's computer will take 2,000 units of time. So if Pat's computer is using 1 unit of time, my computer would be using 2,000 units of time. Okay, so the boss says, oh, there's no comparison, Tech, you better start packing. You go like, wait, hold on a second here. Let's make the problem bigger. How much bigger? Well, let's try the next size up, which is, 2 times the previous problem size minus 1, plus 1, plus 1. Okay, because minus 1 would just be getting back to what we had before. So with linear search, Pat's computer is really just doing the same amount in the worst case. Right? Because, if what you're trying to find is the last item in the array, in the worst case, well, that's going to be just be linear to the problem size. Tech's computer is a little different. Because I'm using binary search, So the whole idea of binary search is you do not start from the beginning nor the end. You start right in the middle of the entire array. You take whatever is right in the middle and you compare. Well, depending on that comparison, it's either greater than or less than. But either way, you throw away 1/2 of all the available items in the array. So in the case that we have 3 items in the entire array, you take away the middle one, but you also take out one other one. So we only got one left, right? So 2 cycles is what I need. So I need 4,000 units of time to do that. Okay? And the boss says, well, guess what? The gap is actually widening. Okay? Are you really sure you don't want to start packing? Because it's getting close to 5 p.m. The security guard needs to go home. Okay. We go like, well, let's make it bigger again. So we use this number, multiply that by 2, add 1 to it. Now it's 7. So, with Pat's computer, it's easy. Okay, it's just whatever that thing is. With mine, it's actually easy too. Okay, because I'm just adding another 2,000 to whatever I have here. Why? Because if you have 7 items, you look at the middle one, you take away, if it doesn't match, you're taking away the one in the middle and 3 other ones. So you only got 3 left. Well, we already know how much time it takes for an array with 3 elements, which is 4,000. So with one additional comparison, I can handle like approximately twice the amount of entries in the array. But if you look at the absolute value between these two, it's still widening. Okay, so I keep doing this. Okay, so we can now use the spreadsheet tricks. Okay, go a few rounds. Okay, so with a 63 element array, the gap is still pretty big. I mean, it has not even started to narrow yet. Okay, but you can see the growth rate is different. On Pat's column, everything is doubling. Okay, with my column, it's just linearly increasing. Okay, so that means eventually, I think it's going to take like 13 columns or so, 13 rows. Nope, not quite. Okay, so Pat is sweating right now. And I'm just containing my giggles. And then just go like, done. Okay, so what is going on here? Well, what is going on here is the shape of the curve is different. The curve for me is actually not linear. If you look at what is the relationship between the problem size and the time that my computer needs, it's logarithmic. Okay, Pat's computer is the one that is linear. But because of the shape being different, my computer eventually will catch up. It doesn't matter how slow my computer is. It will catch up. Okay? So let's just say that, we got a few minutes left. So let's just say that, Pat is not happy about this result and say that, tech has got 20 years to 30 years to soup up his computer and cheat and stuff like that, right? As if there are ways to soup up a computer processor from the 1980s. I mean, Pat's Fitbit probably has enough processing power to beat my computer anyway. Okay, so let's just say that was not fair, and we have to roll the time all the way back to the Apple II computer using a 1 megahertz 8-bit processor. Okay, that's got to be really slow, right? So let's just say that, my disadvantage is now 40,000, okay, relative to Pat's computer, okay? So now you can see all the numbers are going to change, just a little bit, okay? So Pat is laughing and go like, there's no way I can lose now. Well, we just have to make it bigger. And you can see the crossover did not even move much. Okay, it was here before. No, it was here. Okay, and we just moved it down 5 notches. And once again, my little, so it was here. So my little 8-bit, 1 megahertz, computer beat the i9 computer, the i9 processor computer, because it has nothing to do with the hardware. It really has nothing to do with the hardware. It only has to do with the algorithm itself. Okay. The other way to look at this is it will only take 33 comparisons if you compile one huge table for everyone who is alive on Earth at this point, which is 8 point something, 7 point something billion, I think, at this point. 7.2. So it's less than 8 billion. So 8 billion only takes 33 comparisons. Within 33 comparisons, I can either find a particular record or I can confirm someone is not on the list. Okay? So you ask, oh, but what if the world population doubles again? Okay? Because all that climate change is going to increase your crop output, right? So we can feed more people. So the world population can easily increase to 16 billion. So how many times do I need to search, or how many times do I need to go through the loop to find a particular person? 34. Just one comparison more than the one before. So that is the power of binary search. Okay, because the number of times you search is doubling the capacity of the array. Is that okay? This is what we're going to study. Okay, we are basically studying the trend, or how fast something is increasing based on or relative to the size of the problem itself. Are we good so far? All right. So go ahead and read the module. Today I did not get into the details because I knew you guys would not have time to read first. Okay, so read about it on Wednesday when we come back. Then we'll start to get into the math stuff.
Yeah. Clear? So if you put in something like 3, 3, you would get out ABC.
Yes.
Okay, cool. All right. Before I got started, I want to make sure.
Yep, you're correct.